In this video, we will demonstrate a peak modeling experiment with two independent variables. This is an IC ion chromatography study with 6 cations. There are 16 chromatograms in a 4x4 matrix where the concentration and the additive PDCA were varied. In this video, we will demonstrate an experiment that required close to a month to analyze with PeakLab's predecessor. In this video, we will accomplish a much more comprehensive analysis, and we will do it in minutes. If we view and compare the lowest 5 parts per million concentration data sets with the 4 levels of the PDCA, and if we zoom in just the first fronted peak, we will see the no additive peak. We'll see the standard level of additive, we'll see the 1.5 level, and we'll see the 2x level. Looking at this, we see that the additive does not appear to alter the peak shape in any obvious way, but it certainly dramatically changes the elution time. If we view and compare the standard additive level at the 4 different concentrations and we zoom in just the first peak, we see as we go from 5 parts per million to 10 to 25 to 50, a massive difference in terms of the peak shapes. And we will see the same thing if we look at the very tailed peak, the most tailed peak as opposed to the most fronted. Here again, there is the lowest concentration, there's the 10, the 25, and the 50, and we see the peaks becoming sharply tailed, almost right triangular as the concentration increases. So the concentration is having a huge effect on peak shape. And we'll note that any test of a chromatographic model should vary concentrations and include at least some portion of this nonlinear regime where the chromatographic fronting and tailing is visibly discernible. We use the local maxima fitting option. Since each peak in this experiment is baseline resolved, we begin with data that have already been baseline corrected in PeakLab. We will fit the once generalized HVL model with the GE instrument response function. This is our go-to model since it offers third moment asymmetry in the core density, allowing us to fit the HVL, NLC, and a variety of other shapes. And the GEIRF is a general one that includes one probabilistic component, a half Gaussian, and a kinetic component, a first order exponential. This model is likely to manage most non-gradient analytic peaks in virtually every type of chromatographic data, including HPLC and UHPLC, quite well. It's our recommended point for fitting analytic peaks. With 6 peaks detected in each of the data sets with the current settings, we begin the fitting using the most advanced of PeakLab's fitting strategies. Each peak will always fit a separate area and location. Here we also fit separate widths, separate chromatographic distortions. Only the third moment peak asymmetry, which is A4 in this model, and the 3 parameters of the IRF, which are A5 to A7, are actually shared across all of the peaks. These data sets are large, 10,000 to 20,000 points each, and as such the fitting will not be immediate. Also, using this most extensive of the fitting strategies performs a large number of separate fits to ensure the optimal global solution. For complex fits, you will likely want to use this advanced fitting. even if it increases somewhat the overall time for the fitting. At this point, the fit is now complete for all 16 of the data sets. This required about 3 minutes on a slow 4-core machine. It will be proportionately faster on an 8, 12, 16-core machine, since the multi-threading in the program will use all of the capacity in the processor. You will note here, if we look at the merit in the values from the fits, 9 of the 16 are below 10 parts per million error. And here again, a 10 part per million error is an R squared with 5 nines after the decimal point. The worst we see here is less than 20 parts per million. For the immense differences we're looking at here in peak shapes, these are superb fits. As a reference point, fits to a pure HVL model will vary between, for this data, between 2100 and about 4600 parts per million error. Just these 4 additional parameters, 1 asymmetry parameter shared across all of the peaks, 3 IRF parameters also shared across all the peaks, make this profound a difference in the accuracy of the fitting. One of the advantages of fitting convolution models is that we automatically perform an accurate and noise-free deconvolution. In this review, we will display 2 deconvolutions. One, the peak with the IRF removed, and the other with both the IRF and the all third moment non-ideality removed. This will be the pure HVL peak that would exist if there were no IRF and no asymmetry in the HVL's core density. We will first look at the lowest concentration of the most fronted peak, a lithium, with no additive. The white curve is the peak as registered by the instrument. The red curve is the peak with the IRF removed. The green peak is the pure HVL model. We see here that there is very little difference between the pure HVL, the green peak, and the red peak with the IRF removed. On the other hand, there's a large difference between the observed peak and the peak absent the instrumental distortions. Next, we'll look at the highest concentration of this most fronted peak. Here we see a much more pronounced difference between the red peak without the IRF and the green HVL. The peak without the IRF shows a strong curvature, where such cannot exist in the HVL. You can see the curvature in the observed data, and this is not an effect that an IRF can model. Only the asymmetry in a third moment bearing once generalized chromatographic model can do this. We note that the IRF is considerable, especially in the tail. And this is also a good point to note that we have never seen an analytic peak in an isocratic separation where the IRF was negligible. In this next step, we'll use the Explore option to visualize the response surfaces to discern parametric trends. We click the Explore option, and then we select the 3D gradient plots. We then set the response variables that we have already input for the concentration and for the additive level. And also, to keep things as simple as possible, we'll only look at the first peak's surfaces. There are 3 types of bivariate response plots. You can plot a 2D contour, you can plot a 3D shaded, or you can do a 3D gradient plot. I'll use all of these as I review the parameters from this study. I'll begin with the A0 area parameter. Although the area should be linear with concentration and independent of additive, there is a small effect from the additive. If we look at the center value, we know there's going to be a massive effect from the additive, since its purpose is to produce significantly earlier elution times, and that's precisely what we see here. There is, however, a small concentration effect as well. The effect of such is that the center slightly diminishes with concentration. At this point, I'll change to a 3D gradient. We're going to look at the width. I'll animate the surface. We know the widths increase with elution time in the column. The additive, because it's producing a faster elution time, should produce lower widths, and it does. The concentration also increases the width, however. Here I'm going to rotate the center wheel of the mouse to try to produce the best visualization of that effect as well. So you can see the concentration is also producing larger widths across the surface. We're now looking at the A3 chromatographic distortion. This is the tailing and the fronting that are estimated in the HVL and NLC models and their generalized extensions. This is an astonishing efficacy of modeling here. This chromatographic distortion, despite describing a higher moment skewness, is about as perfect a surface as one could hope to see with real-world chromatographic data. Now the fronting is at its maximum with zero additive and at the highest concentration. Because the fronting is a negative value for the distortion, this is the point right here at a zero additive level, maximum concentration, where we see the highest measure of the fronting. We see the least at the lowest concentration and at the highest additive level. We've thus far only inspected the parametric surfaces for the first peak. Since these 4 principal parameters are fitted for all 6 peaks, there are 5 more sets of surfaces. For the remaining parameters, however, which are shared across the peaks, there's but a single response surface. I'm going to start by clicking on the 3D shaded surfaces, and I'm going to select the 3D rendering option. And instead of interpolating, we're going to do a fast smooth, and I'm going to select the highest count, which is like an all neighbor smoothing, which is a global smoothing using all of the data. And we're doing this because these higher parameters, which are the higher moment parameter and the IRF parameters, which are shared, tend to be noisier, and you'll see trends easier if everything is smoothed. We're going to look at the A4, the asymmetry, and here we see that we have a fairly good trend, at least when you're looking at the smooth data. The asymmetry in the model's core data increases with both concentration and with additive level, and it seems to be a fairly well-defined trend. If we look at A5, this is the IRS probabilistic half Gaussian component. We believe this to some measure maps axial dispersion. If that is the case, this smooth plot suggests this parameter is indeterminate with respect to additive, but generally increasing with concentration. It's certainly a noisy plot. If we look at A6, this is the IRF's kinetic component. We believe this maps the flow path and detector delays and distortions. The surface is an especially well-defined one, this parameter diminishing with concentration and increasing with the additive level. It's a very accurate IRF parametric plot. The last of the parameters is A7. This is the fraction of the area fraction of the probabilistic component of the IRF. Even though we can see a little bit of a trend here, we look at the values and we go from 0.62 to 0.65. Basically the parameter is effectively constant across all of the fits. One more item I will show here. With some experience, you can use this animation as I'm doing here to get a complete picture of the parametric relationships in an experiment, and you can see it's all within a single vision. You have your A0, A1, A2, A3 core parameters, you have your asymmetry and your IRF parameters, and you get a clear picture of what the chromatographic model is doing across all of the data sets in the experiment.